When we have a series like 1 divided by n to the p, which means when n is 1, we get 1 divided by 1 to the p, 1 divided by 2 to the p, 1 divided by 3 to the p, and then all the way up to n minus 1 to the p and n to the p. This is called a p-series, and 1 to the p is just 1, and so we get 1 plus 1 over 2 to the p, 3 to the p, and so on. And we have a claim, and here we'll make the assumption that p is positive or greater than 0, because if p is negative, then this becomes infinity anyway. So here we have the claim that the p series, it converges if p is greater than 1, and the p series diverges if p is between 0 and 1, including 1. And here's the proof. And so we use the integral test. The corresponding continuous function is 1 over x to the p. 1 over x to the p can be rewritten as x to the negative p. The antiderivative of x to the negative p at 1 to the exponent, and so we get negative p plus 1, and then dividing by negative p plus 1. Negative p plus 1 is the same as 1 minus p. So we write negative p plus 1 as 1 minus p. And then we evaluate from 1 to b. In the place of x, if we put b, then we get 1 minus 1 over 1 minus p times b to the 1 minus p. And then in the place of x, we'll put 1. 1 to the 1 minus p is just 1. And so this becomes 1 dividing by 1 minus p. This part and this part has a common factor of 1 minus p. And so if we factor out the 1 divided by 1 minus p, then what's left is b to the p to the 1 minus p, and then minus 1. And this is just a constant. The limit is with respect to b. And so we can move the quantity 1 divided by 1 minus p to the front, out in front. And so we get 1 dividing by 1 minus p times the limit of b to the 1 minus p and minus 1. And so this integral is this. And so once again, the claim is that the p-series converges if p is greater than 1, and the p-series diverges if it's between 0 and 1, including 1. Now let's deal with the case where p is between 0 and 1. If p is between 0 and 1, so if this p right here is a number between 0 and 1, then 1 minus p is positive, because this number is smaller than 1. It's between 0 and 1. So 1 minus p is greater than 0. And so the limit of b to the 1 minus p, but 1 minus p is a positive number. And so if b approaches infinity, then b with some positive exponent will also approach infinity. And so now we have 1 dividing by 1 minus p. As b approaches infinity, this quantity will approach infinity. So we get infinity minus 1 is infinity, and then times this finite value right here, which is infinity. And therefore, the integral of 1 divided by x to the p for p between 0 and 1 is equal to infinity, and therefore it diverges. And so by integral test, we know that this series right here the p series here diverges also. Remember that the integral test says that if the integral of 1 divided by xp diverges, then the infinite series also diverges. So when p is between 0 and 1, the p series diverges. Now let's look at the case where p is 1. If p is 1, then we get 1 divided by n to the first, which is just n. But the series 1 divided by n is the harmonic series, and we know that harmonic series diverges, and therefore 1 divided by n to the p with p equal to 1 diverges. So we have shown so far that if p is between 0 and 1, including 1, then the p series once again, this is called p series diverges. Now let's look at the case where p is greater than 1. So let's look at some examples first before we get to the case with p greater than 1. If we have a limit of b to the positive 2, as b approaches infinity, then b squared will also approach infinity. If we have b to the negative 2, b to the negative 2 is 1 divided by b squared. And so as b approaches infinity, b squared approaches infinity. And so we get 1 divided by infinity, which is 0. So if the exponent is positive here, we get in positive infinity. If the exponent is negative, we get 0. So same thing here, if we have b to the 0.5, this exponent is positive. So as b approaches infinity, this quantity right here also approaches infinity. But if the exponent is negative, then it can be rewritten as 1 divided by b to the 0.5. This bottom part here approaches infinity, so we get 1 divided by infinity is 0. So in general, if we have b to the with the exponent k, the limit will equal to infinity if k is greater than 0 or k is positive. the limit of b to the k is equal to 0 if k is negative or less than 0. So once again, if the exponent is positive, we get infinity. If the exponent is negative, we get 0. Alright, now we're going to deal with the case with, and then for the case where p is greater than 1, if p is greater than 1, then 1 minus something greater than 1 is negative. And so 1 minus p is less than 0. And so we have limit of b with an exponent negative, then this is equal to 0. The integral of 1 divided by x to the p, we worked this out earlier and it comes out to be 1 minus 1 divided by 1 minus p times the limit of b to the 1 minus p minus 1. The limit of this quantity, because 1 minus p is negative, the limit of this quantity will be 0. And then limit of 1 is just 1. So we get 0 minus 1 is negative 1. And negative 1 times 1 is negative 1. And therefore the integral 1 divided by x to the p is equal to negative 1 divided by 1 minus p. So for example, if p is 2, which is greater than 1, then we get negative 1 divided by 1 minus 2, which is 1. If p is 3, then we get negative 1 divided by 1 minus 3, which is negative 2, and which comes out to be 1/2. And therefore this integral right here converges. Then we know that by the integral test, the p-series also converges. So the integral test says that if the integral of 1 over x to the p converges, then the infinite series of 1 over n to the p also converges. And so in summary, if we have a p-series, if p is between 0 and 1, if p is between 0 and 1, including 1, then the p-series diverges. And if p is greater than 1, and then the fix this. If p is greater than 1, then the p-series converges. So if p is between 0 and 1, then p-series diverges. If p is greater than 1, then the p-series converges.